Quantum levitation involves two things: a magnet and a superconductor, usually with an insulating pack of liquid nitrogen to keep the superconductor cold. A superconductor is a material that transfers energy with near to perfect efficiency. Electric and magnetic waves pass freely through a superconductor, so what happens? As fast as the charge contacts the material, the charge also wants to exit the material. The charge moves in the direction of the material, but the material is at the same time expelling it as quickly as possible. This is called the Meissner effect, the expulsion of a magnetic field from the interior of a material that is in the process of becoming a superconductor. These two forces cancel each other out. The magnetic field slips around the superconductor instead of going through it. This creates a pocket in the magnetic field. So how does the superconductor in the video simply stay in place? Quantum locking is the answer. The further a magnetic field has to penetrate a superconductor, the more it is repelled. In most cases, the magnetic field is repelled completely because it lacks the energy to overcome the Meissner effect. But in these particular demonstrations, the superconductor is extremely thin, in the realm of microns, which means the magnetic field is able to overcome the Meissner effect. But this doesn't happen everywhere on the superconductor. There are certain areas of the material that are thicker and thinner. Impurities act as weak points, where the magnetic field can get through easier. These weak points cause a magnetic field to bunch up, like water going through a strainer as it passes through the superconductor. These are called flux tubes, columns of magnetic energy that pin the superconductor in place within the magnetic field. Any motion of the superconductor requires energy in order to realign the flux tubes, so the superconductor naturally wants to stay where it is at. Quantum levitation.
When an electric current is passed through a conductor, some of the energy is lost in the form of heat and light. The amount of energy lost varies depending on the individual material's electrical resistance. Some materials, like copper and gold, are great conductors of electricity and have very low resistance. Scientists discovered that the colder these materials are, the more conductive they become. In 1911, when scientists cooled a sample of mercury all the way down to 4.2 degrees above absolute zero, its resistance abruptly disappeared. The first superconductor had been discovered. Gradually, more and more superconductive materials have been found that show zero electrical resistance below a certain critical temperature. And when resistance is zero, electricity is conducted perfectly without any loss, and a current can theoretically flow in a closed loop forever. This has been demonstrated by scientists who have sustained electrical currents in superconductive rings for years without any measurable depreciation of energy. And it doesn't end there. Not only do superconductors have absolutely zero electrical resistance, they also don't like to let magnetic fields pass through them. Instead, the field remains at the superconductor's surface. This expulsion of magnetic fields is known as the Meissner effect. You've probably seen the Meissner effect in action in science experiments that look like this. A magnet is set on top of a superconductive material, and at room temperature, nothing really special happens, but when the material is cooled down to its critical temperature, the Meissner effect kicks in, causing the magnet to levitate, as if by magic. But superconductors can be used for much more than cool science tricks. These materials are used today in MRI machines, super fast floating trains, and even particle accelerators. But we can't forget that these superconductors have to be kept at temperatures near absolute zero in order to function properly. This is a main limiting factor in the practicality of superconductors. Fortunately, scientists have been busy finding and creating materials that become superconductive at higher and higher temperatures. For example, some ceramic materials undergo a superconducting transition at high enough temperatures that they can be cooled down using relatively warm liquid nitrogen. These materials are known as high-temperature superconductors, and they have revolutionized how and where we are able to use this technology. But still, always having to have liquid nitrogen at hand is extremely limiting. The goal for scientists is to create a material that is superconductive at room temperature. If we had room temperature superconductive wires for electronics, we'd be able to power devices using much less power. None of the energy would be lost as heat, changing the way the electronics are designed and built. This technology would allow for smaller and much more efficient devices. In 2015, researchers observed a material that, when placed under extreme pressure, became superconductive at around -70 degrees Celsius. This set the record for the highest temperature superconductor, but as of now, room temperature superconductors haven't been found.
So we have quantum locking. The superconductor is locked in space, and it stays wherever I put it. This is quantum trapping.
Liquid nitrogen.
Upside down.
Right.
And it stays locked. Because this is symmetric, it can rotate without break the locking. You see, if I can move it on the side, it will again pivot around the axis of the magnet. I just levitate it, and I can just rotate it.
So it's actually floating above the surface.
Yeah, it's not floating, it's locked above the surface.
So you could tilt it at an angle and it would
Yeah,
still fly
I can do
around.
it like this, and it will just go around like this. Because I go and put it at different height, put them in like this.
And lock it at the height.
Lock
right?
it, yeah, different height, different configuration. If you could just hold for a minute. High. Locking it upside down, and then it is suspended.
Fantastic.